We measure the temperature. Okay, you not raise the number immediately after you put the thermometer into the object. Okay, you need to wait some time. Especially when you measure the body temperature, you need to wait quite a long time. Okay, to reach the thermal equilibrium. Another thing you need to pay attention to is that what happens precisely about those molecules when you have this thermal equilibrium. So what happens is, if you have some like cold object and hot object, okay. So we know that the molecules here is less energetic. The molecules here, in average, have more energy, so they are moving faster. The molecules here moving slower. So if you bring them into contact, okay. So at the contact surface, the molecules will collide with each other. So when the collision happens, the energy will transfer from the high energy molecules to the low energy molecules. Okay. So that means when during this process there are some energy transfer from the high energy object to the low energy object. High temperature object to the low temperature object. Okay. So this kind of energy transfer is called the heat. Okay? It's called the heat. So heat is an energy transfer from the high temperature object to the low temperature object. Usually we use Q to denote it. So this is a high temperature object, this is low temperature. But when during this process more and more heat extracted from here and put into here. So the temperature of this one decreases, temperature of this one increases. So finally, they will reach the same temperature. After that, there is no energy transfer. Okay, heat is transferred due to the temperature difference. If there is no temperature difference, then you wouldn't have the heat transfer. Okay, so that's heat. Okay. Here, for the energy transfer, for the heat and energy and the temperature, I will talk something about. Temperature is a measure of average kinetic energy. It's not the total kinetic energy. Okay. And the average kinetic energy, roughly speaking, it should be the total kinetic energy for the object divided by the number of molecules or atoms. Okay. So please note that here it depends on the average kinetic energy, not the total kinetic energy. For example, if you have a small cup of hot water, and then you have a large cup of cold water. Okay, which one has a larger temperature? Hot water, cold water, which one has a larger temperature?
Cold water.
Hot water. Temperature, it means hot or cold, right? So this T1 should be larger T2. But now, if we consider the total energy, which one has a larger total energy? Usually it should be the cold water, because that if you have, this is much larger size. Okay. So the total energy for this one should be larger than total energy for this one. Okay. So you see, temperature has nothing to do with the total energy. This one has a total energy because it has a lot of molecules. How about the average kinetic energy for each molecule? Which one is larger? Cold water or hot water? Hot water. So average E, this one is larger than this one. Okay? Because it has much more less molecules. Okay? So that's something we need know more about relation between the total the temperature and the average energy, total energy. Okay. Let me think about this conceptual understanding. Okay. Because we all also have the conceptual problem. Now, let's talk about the zero slope of thermodynamics. The statement of this zero slope is quite funny. It says, if A and B are separately in thermal equilibrium with object C, then A and B are in thermal equilibrium with each other, even they don't really touch with each other. The statement here can be translated into temperature like this. If TA equals to TC, okay, if you have three objects A, B, C, and you know TB equals to TC, this law says that TA has to be the same TB, okay. Mathematically, it seems that I'm talking about some trivial stuff. A equals to B, A equals to C, B equals to C. Of course, A equals to B, okay. But because temperature is somewhat complicated thing, we don't really know if you can simply apply that if temperature, if object A and C has the same temperature, if object B and C has the same temperature, can you just say A and B has the same temperature? That cannot be guaranteed by maths. Okay. It can only be guaranteed by experiment. And after many experiments, we see that this is true. So we accept it's a law. And it's called the zeroth law because before people established this as a law, we already have the three laws of thermodynamics: the first law, second law, and third law. After that, we established this as a law, but and we feel that this is very fundamental. Okay, it's kind of some fundamental definition of the temperature. So it has to be put before the first law. How can you put how can you call it? The only way is called the zeroth law. Okay. So that's why weird name, zeroth law. And I hope we wouldn't find more fundamental law in front of that. If we have to put some words before that, it will get us trouble. How can we call that? Negative first law? That's even horrible. Okay. But I guess not. This is already very fundamental, so we wouldn't put any law before that. Okay, so let's stop here.